should start. It's a great pleasure for me to introduce Alan Weinstein from Berkeley and Stanford, who will talk about failure of twisted Poisson property for monopole plasma.
Well, thank you very much. It should be very exciting for me. This is the first talk of this kind that I've ever given. Well, I gave one video talk once at a meeting in India, but it was a very different situation. In particular, I couldn't see anybody else. And I couldn't share my screen. So I will immediately try to share the screen with an image of the paper that, do I have to start up the screen sharing again? Mm-hmm. Start broadcast, here we go. How's that? Let's see. You get to see my front page. Okay, there we go. This is the paper that is the basis for this talk. It's a joint work, as you can see, with Manuel Lines and Cristina Sardone from Madrid. And that's the publication date and the, let me see how I can. I'm trying, there we go. There's the spotlight. Along the side, I put in the archive information in case you don't have access to physical review. So this was, in some sense, this goes back a long way in Poisson geometry. This paper was inspired by a talk that I heard given by Phil Morrison, who introduced himself to you a few minutes ago, about a year and a half ago. And in this talk, he described how the presence of magnetic monopoles destroyed the Jacobi identity in a bracket for the so-called Vlasov-Poisson equation. This bracket was originally found by Phil in 1980, and Jerry Marsden and I, a couple of years later, figured out a much more geometric construction of the bracket, which as a kind of reduced, as a symplectic reduction, which incidentally made for a slight correction in Phil's formulas. But basically the idea came from Phil. And for me, this was the beginning of Poisson geometry. In fact, it was a result of this project, which involved the Poisson structure on the dual of a Lie algebra coupled to something else. This is really what got me interested in doing Poisson geometry, and I wrote that other paper about a year later. And interestingly, one of the people, so the conference was in honor of the retirement of Robert Littlejohn, a Berkeley physicist, and it was his thesis that led to the thesis of Ted Courant on Dirac structures, and this has led to Courant algebroids and so on. So the plasma physics story at Berkeley really has led to a lot of the geometry that I and I think a lot of you have been doing over the years. So that's kind of interesting. So in this talk, Phil explained how that in the presence of magnetic monopoles, the bracket that he had written down and that one that Jerry and I had written down no longer satisfied the Jacobi identity. So it wasn't really a Poisson structure, and he gave various things that then went wrong when you tried to apply this to building physical models and so on. So sitting there listening, I had the idea that maybe we could salvage something and find a so-called twisted Poisson structure. Find that this was a twisted Poisson structure. Roughly speaking, a twisted Poisson structure is given by a bracket bilinear over the bi-derivation bracket, so bi-vector field, for which the Jacobiator is governed by a closed 3 form. So for example, if you have a non-degenerate two-form, which is not necessarily closed, then this always, by inversion, defines a twisted Poisson structure where the twisting three-form is just D of the two-form involved. So that was the idea, and I didn't really do anything much with it until Christina came as a visitor in the spring of 2019. And we tried to prove that it was a twisted Poisson structure, and we couldn't. We kept working on it, and finally we decided maybe it's not. So we then began looking for counterexamples, and she went back to Madrid and connected up with a graduate student named Manuel Leintz, and together they were able to, using some formal computer calculations, come up with what turned out to be the counterexample that I will talk about here. So now let me attempt some writing for you. So what I want to do is, roughly speaking, well, I want to talk about I wanted to talk about the particle in a magnetic field. The phase space for this, which turns out to have a twisted Poisson structure. So then I will explain something about what twisted Poisson structures are. Then I'll go on to the example, which is going to be the key example for our specific example, which is essentially the dual of an almost Lie algebra. So G is going to be a vector space with a bilinear bracket on it, which doesn't necessarily satisfy the Jacobi identity. And unfortunately, in this context, in this more general context of a G, the notion of twisted doesn't seem to make sense. And this may be why we are not able to show that G star has a twisted Poisson structure, even though G, so what is G going to be? G is going to be the C infinity functions on X, where X is a twisted Poisson manifold. And in our example, it will be the phase space for a particle in a magnetic field generated by a kind of cloud of monopoles. And then if there's time, I'll give a little more background on Maxwell-Blasov. Because although it seems doubtful, there does seem to be some hope that by going back to these full equations that one can find something that's twisted Poisson structure. And that's the ongoing work by Cristina Sardone and Paola Balsero. So that's the kind of outline for the talk. Now I'll go back to giving some details. Okay. So for a particle in a magnetic field, it's usually described by a Lagrangian formulation where there's a vector potential A and a magnetic field B, which is the curl of A. And then there are Lorentz equations that give them the particle motion, which essentially says that the magnetic force is up to some scalar constant, the cross product of the velocity. I'll use old-fashioned notation with arrows to indicate vectors. So the force is that plus a possible electric force if there's an electric potential field. And it turns out that there are a couple of Hamiltonian formulations of this. In one of them, so let's say M is R3. In one of these formulations, the phase space is just T star M with the usual cotangent bundle symplectic structure. And the Hamiltonian is a kinetic energy term, the usual kinetic energy term, plus an electric potential, which is the pullback of a function from M itself, plus a magnetic term, which is the dot product of one forms with the with this vector potential A. Now, there's another formulation which also makes sense if there's no electric potential and B is simply a vector field that satisfies the one of the Maxwell equations, del dot B equals 0. That's, of course, a consequence of this one. But if we only require this, then we can only locally set things up this way. But it turns out globally, we can completely get rid of the electric potential by changing the vector field, changing the symplectic form to an omega B, which is omega T star M, plus pi star of B. And now I have to explain what this B without an arrow above it is. Well, if we're in the 3 dimensions, then we can contract the vector field B with the volume element, which was considered part of the structure here, to get a 2 form. And so we can consider B as actually a 2 form and the potential A as a 1 form under these identifications. And so in the case where there's a potential, B is equal to dA. But in general, this equation here simply translates into dB equals 0. Okay. So in other words, if we are dealing with this kind of situation, we're in ordinary Hamiltonian mechanics. But now, if there's a monopole density around, if there's a field of Dirac monopoles, which we'll assume to be a continuous density, just like it's common to assume a continuous charge density, even though the charges might actually be electrons. This could be a function which is a monopole density. And what this translates into is that dB is no longer 0, but it is phi. It's a 3 form phi, which is essentially mu times the volume element, or actually pulled back. It's the, well, no, this is dB, and then the then d omega b is the pullback of dB, or, okay, so let me write this, and I'll call this phi, the pullback phi. So this is exactly the situation of a twisted Poisson structure, because if we let pi, now I'm going to write a capital pi, be the Poisson structure, or the bracket you get by inverting omega b, then it turns out that pi bracket pi is no longer 0, but rather it's the pullback again. Well, oh, no, I'm sorry. It's wedge 3 of pi tilde. So pi tilde maps cotangent vectors to tangent vectors. So wedge 3 of it maps 3 forms to trivectors. And we apply this to the 3 form phi, which is certainly closed because it's dB in this case. So this is saying, this is exactly what, this is exactly the definition that Pavel Cervera and I gave a number of years ago of what we called a twisted Poisson structure. The idea was already basically around, maybe not quite so explicitly, in string theory. And there are some things you can do with twisted Poisson structures that you can't do with just arbitrary bivector fields. For example, most important perhaps, the twisted Poisson structure is associated with a Lie algebroid, which is in fact a Dirac structure for a twisted Courant algebroid, twisted by phi. I won't go into details about that. So twisted by this, or actually by yeah, twisted by the 3 form phi. Since it's a Lie algebroid, the image of this pi tilde gives an integrable distribution, and the leaves, which are in the Poisson case, are symplectic structures. In our case, are non-degenerate closed. I'm sorry, non-degenerate 2 forms, which are not necessarily closed. So those are sometimes called almost symplectic structures. So an almost Poisson structure will be any pi, any bivector field pi at all. It's twisted Poisson if it satisfies this, and it's Poisson if pi bracket pi is equal to 0. So almost symplectic is an example not only of almost Poisson, but of twisted Poisson. And twisted Poisson, foliations with almost symplectic leaves are examples of twisted Poisson structures. So in our case, we're going to be dealing with the non-degenerate case. So there's only one leaf, which is, well, at this point, only one leaf. But we now are going to look at the case of so-called plasmas. And for our purposes right now, a plasma is given, roughly speaking, a plasma is given by a distribution in phase space, a probability distribution. You can think of a large cloud of particles with moving in different directions with different velocities or different momenta. And all of them together are described, just like a fluid is described by a density of particles in configuration space. A plasma is described by a density of particles in phase space. So whereas in a fluid, all the particles in a given place are more or less moving in the same direction, in a plasma, you have particles going in all directions at all places. So it's described by a it's described by a density, which is we can think of in the dual space of C infinity of x. And on C infinity of x, we have the Poisson bracket, so I'll think of this as an almost Lie algebra G. So therefore, on G star equals D, we have what we could call a Lie Poisson bracket. And it's determined by the equation that the bracket of A and B is equal to the Lie bracket of A and B, where A and B belong to C infinity of X, I'm sorry, but they belong to G, which we think of as a subset of C infinity of G star, given by the linear functions. So this is the usual formula that defines the Lie Poisson bracket when G is a Lie algebra. It defines it because you assume that it's a biderivation. And so the bracket of two things at each point is determined by their derivatives at that point. And the derivatives of that point are always the derivatives of a linear function. So anyway, given any almost Lie algebra structure on G, which is simply a skew symmetric bilinear operation, we get this Lie Poisson bracket on functions on the dual space. So the question is, it's well known that if the bracket on G satisfies the Jacobi identity, if this one satisfies the Jacobi identity, then obviously this one does on linear functions, and then it's easy to show that it does on all functions. So this is a well-known construction, actually, due originally to Lie of the Poisson bracket on the dual of the Lie algebra, whose symplectic leaves in our current terminology are the coadjoint orbits.
Alan?
Yes.
So this bracket, which will not be now a Lie bracket, but it's still linear, is it right?
Yeah, it's still a biderivation. Yeah, it's given by a if you want, you can say it's given by a bivector field on this space of densities.
But by the way, it's also a linear, like the linear in the sense as the KKS bracket is linear.
Yeah, it's linear. It's linear with regard to multiplication by constants. Is that what you mean? Yeah, it's not linear with respect to multiplication by functions because there's this derivation law.
Okay, thank you.
Right? I mean, we have if I multiply G by F, I get one term, which is this, which is all you would have if it's linear for functions. But then there's one more term, which is the other term in the Leibniz identity. So it satisfies that, but not the nothing more.
Okay, thanks.
Alan, I think he means linear as a linear bracket, linear in the the coefficients being linear.
Oh, linear in that sense that if you were to write down the CIJK, so to speak, that it's linear on the phase space itself. Yeah, sure, that's still the case. Sorry, Anton, and thanks, Henrik, for explaining. So the question then is, what if we start with an X with a Poisson bracket, which is twisted Poisson? That leads to a Lie algebra of functions, which is, well, it leads to an almost Lie algebra of functions, and it's not clear how to translate into just the abstract bracket of the abstract bracket on G, the fact that X was twisted Poisson. And that's one of the things that already made us start to wonder whether this bracket on G star was itself twisted Poisson, because we'd have to somehow take the 3 form on X that made the structure there twisted and build out of it a 3 form on D. And we never could quite figure out how to do that. We got some candidates and they never quite worked out. So we finally wound up with a counterexample. And let me say something then about the counterexample. So for this, I'm going to attempt to, so the counterexample is in this paper that I mentioned earlier. And let's see, is this right? Oh, sorry. Okay, here we go. Here it comes. So here's the example. So M, our configuration space, will be the usual R3, and the coordinates are X and P. And omega is going to be the sum of the usual cotangent bundle symplectic form plus the pullback of something from the base. And this form there is, okay, so you notice that this is a 2 form. It's this, wedge that. So it's a 2 form on the base, meaning it depends only on the X coordinates, pulled back to the total space. And it was Christina and Manuel that came up with this example after playing around with many things. And there's no particular interpretation of it. But in any case, the corresponding bivector, it's always the case that when you have a pullback of a 2 form from the base, the resulting change in the standard Poisson structure is adding non-trivial brackets between momentum variables. And the non-trivial bracket is exactly a sort of mirror image of the pullback 2 form from the base. Now it turns out for this, let's see, I'll make it, can I make it a little larger? Yeah. That the d omega b is not 0, it's just this. And the Poisson bracket, I guess there should have been in general, there's a formula where the Poisson bracket, or where the the Schouten bracket of Sn is Schouten. The Schouten bracket of the bivector with itself is minus wedge 3 omega to pi tilde of the d omega. Anyway, it's this. So you can either compute that directly, or you can use the fact that it has to satisfy equation 3. This is actually from the paper with Christina and Manuel. So 3 was an equation, the equation I wrote earlier in the talk relating pi bracket pi to phi. Okay, so F, so I left out a couple of general things here. So F is going to be F is going to be the point in the dual of this almost Lie algebra, where we're going to show that we can't have twisted Poisson. And for that, I have to go back and explain a little more background. So, first of all, as I said earlier, in the case of a twisted Poisson structure, we have a Lie algebroid. Which is again the graph of pi tilde. Pi tilde goes from T star. Well, I'll call it, well, it's actually T star X to TX, right? Where in our example, X is going to be the, well, there are two possibilities. Either X is the phase space, the R6, or X is this space of densities. But in any case, if we have a twisted Poisson structure, this thing becomes a Lie algebroid. And what it is it's a Dirac structure in Tx plus T star X twisted by phi. What that means is that the Dirac bracket of two vector fields has an extra term in T star X obtained by contracting the two vector fields with phi. Okay. And that implies that the image of pi tilde is integrable. So in order to prove that something is not twisted Poisson, it suffices to show that the image is not integrable. And in fact, there's a partial converse. If we have an almost Poisson structure of constant rank, and if the image of pi tilde is integrable, then in fact you can find a 3 form that makes it almost Poisson. And that was the work of Paula Balsero and a collaborator whose name I'm not coming up with immediately, but there's a reference to it in the, well, okay, let's find the reference. Here it is. Paula and El Garcia Naranjo on gauge transformations, etc. So this is the reference list from the paper that's the basis of this talk. Okay, so we're going to show that, and for this, to show that non-integrability, to show this, it suffices to find an F in G star. So now we're going back in the case where X is the dual of the Lie algebra of functions. And A and B in G, which is this, almost Lie algebra of functions, or such that the bracket of the Hamiltonian vector field of A with the Hamiltonian vector field of B at that point F is not HC of F for any C in G. Now, of course, the Hamiltonian vector fields of linear functions are not all the possible vector fields in this distribution, but at least they have all the possible derivatives of such vector fields. And that's why it's sufficient to show the sort of non-integrability in the case of linear functions. So our example is going to require finding a bunch of functions that have properties which contradict integrability. Okay, now what we're going to use is the following fact about almost Poisson structures, that if you take the commutator bracket of two Hamiltonian vector fields, then you get, in addition to the usual term, the Hamiltonian vector field of the Poisson bracket of those functions, there's another term which is pi tilde of phi of HA, HB dot. This is actually the extra term. This is actually, remember, the extra term in, this is the one form that's the extra term in the Courant algebroid, the twisted Courant algebroid, and we apply pi tilde to it. It's more or less, I think, just saying that we have a Dirac structure in this twisted Courant algebroid. Okay, now of course this is a Hamiltonian vector field. So it's going to suffice to show that this term here is not HC for any function C. Okay, so that's the first preliminary. So what we're going to do is we're going to find an F, an A, and a B such that when we do this contraction, we apply this at the point F, it is it's not a Hamiltonian vector field at F. Now, how are we going to do that? Well, first of all, we're going to use we can identify densities with C infinity of X by using the volume element, the usual one, which is wedge 3 of omega. Sorry, I'm losing my voice. I hope I can make it through the rest of this talk. Okay. Now, this identification wouldn't be useful if it weren't for the fact that this volume element is invariant under all Hamiltonian vector fields, which you can check that it is. So even though omega b itself is not invariant under Hamiltonian vector fields, that's kind of related to this expression here. The volume element is. So we can identify D with C infinity X. And now we're going to use the following lemma. If G is equal to minus HF of C, or for that matter, HF of C, or HC of F, because remember, these are the negatives of one another. For some C, then the integral of G around every closed integral curve of HF is 0. So this is the lemma that we're going to use, and it's pretty easy to prove this. In fact, it's true when HF is replaced by any vector field psi. The point is that if something is a if a function is a derivative by psi, a vector field psi, and if psi has a closed orbit, then the integral of the derivative around that closed orbit is 0 because the function returns to its original value. So those are the things that we're going to use. And now I can go back to the our specific example here. Let me recall. This was our Poisson structure. That was the Scouten bracket. This is the Hamiltonian vector field of F. So F is going to be this function, x1p2 minus x2p1. And it's Hamiltonian vector field, in addition to the usual term that you would get from the canonical symplectic structure, you get this extra term here. So on each orbit of this, P3 and X3 are constant, and the projections in the X1, X2, and P1, P2 planes each traverse at unit speed circles centered at the origin. In particular, all these orbits are periodic. So we have lots of periodic orbits to try to find one around which the integral of some other function, the integral of some derivative is not zero. And so here now what we choose is A is P3 and B is P1. If you're really interested in the details, I would just, this is just literally copied out of the paper with Leitz and Sardone. For the you do the Hamiltonian vector fields, you choose A is P3, B is P1, you can choose the Hamiltonian vector fields. Remember, the next thing we did was we contracted with the closed 3 form, and we get this, x1, x2, dx2. Then we apply pi tilde to it to get a vector field. And then we operate on the function f, and we get x1 squared. And that integral is obviously not zero because it's a non-negative function. And going back over the arguments that I gave, working your way backwards, that shows that the distribution spanned by Hamiltonian vector fields is not integrable. So our almost Poisson structure is in fact not twisted Poisson. So that's the end of the sort of the main content of what we've done. So maybe I should end by just finish the talk by making some remarks and then ask for questions. But maybe I'll ask right now if there are any questions on what I said.
I think Chen Chan has a comment and Jim have a comment. Maybe they want to make this comment now. Chen Chan?
Yeah, yeah, I can do that. So I was like doing your lecture. I cannot really tell, but I was thinking, especially given the abstraction term is so nice. Do you think, Alan? Do you think like it could be like a 2 Poisson, like it's not a twisted Poisson, but it's a higher Poisson. So it could be like you know, have a 3 bracket, and then this 3 bracket satisfy higher Jacobi.
I think that might be true. Some people have looked at twisted Poisson structures and related them to higher structures. I don't know if Marco is here today, but I think he wrote a paper with Yael Fragier on this sort of thing. There's a whole question of how do you quantize a twisted Poisson structure. If you do deformation quantization, you get a non-associative algebra. You can sort of do deformation quantization with any almost Poisson structure, and you'll get a non-associative algebra. And maybe its failure to be non-associative is not so bad, that is to say its associator, can be explained in terms of the 3 form defining the Jacobiator in the twisted Poisson structure. I've asked around about that, and no one seems to be able to have given quite an answer. There's an old paper of Park, J.S. Park, that looked like it might help, but I looked at that paper yesterday and I didn't find anything there. The other idea of what you do with twisted Poisson structure is that locally, of course, the 3 form, the closed 3 form is D of a 2 form. And you can use the 2 form as a kind of gauge transformation to switch the almost Poisson structure into a Poisson structure. So you get a family of local Poisson structures, which you can each deformation quantize, and then on overlaps have some kind of isomorphisms between these algebras, but they don't quite match up on the intersection of 3 open sets. So you have to do you have to get some kind of stack of algebras. And there is some literature, and I believe that, let's see, well, a couple of our audience whose names are blanking on me have done, they can raise their hand and have done that sort of thing. So there is some possibility that, I mean, there's a possibility that any almost Poisson structure, I don't know, is it true that if you have any Lie algebra, any almost Lie algebra, that you can look at higher terms to make it?
Only if the high term is nice.
Yeah.
But the one you gave, it looks like really neat. So yeah. Okay. Yeah. So.
Okay. Was there another question or comment?
But if the higher term is not nice, is it possible to maybe push the not nice stuff further and further, like higher and higher up, and then eventually get rid of it?
Well, that's
that was Olivier was saying. Oh, so I'm sorry. Olivier was saying that because the distribution is not integrable, so you can use this resolution to make this not Lie algebra into O infinity algebra. So like you probably can resolve some if you don't run into an very bad situation.
Yeah, that may be. I haven't looked in that direction at all, and that's one of the open questions of this problem is, the way I put it is, suppose you start with any almost Lie algebra. What property of this almost Lie algebra would make the Lie Poisson structure on its dual twisted Poisson, as opposed to just almost Poisson? And it may be that it's never the case. I mean, it may be that our example, which took us so long to find, is actually just an example of something that's a general property of Lie algebras that don't satisfy the Jacobi identity, or almost Lie algebras. So the question is there any almost Lie algebra that's not a Lie algebra for which the dual has a twisted Poisson structure? I don't know of any such thing. Maybe, I mean, the examples that that Balsero in several papers have looked at arise from the motion of systems with non-holonomic constraints. And maybe there's an example of such a system where you get twisted Poisson on the level of the the dual of the Lie algebra, or the dual of the almost Lie algebra. I don't know.
There is a question from
go ahead,
from
Eva.
Jair in that direction, concerning this work of Paula Balseiro and Luis Naranjo. They say that their example is in the non-variational setting, and he's asking if you think this counterexample could have some variational principle. Or, I know you said that you found it like by chance, but you think that you could interpret it with a variational principle, or that's the question.
Yeah, that I don't know. Yeah, I guess I don't have any quick answer to that question.
Okay, thank you.
Yeah.
Well, there's Manuel. I see.
I think I can answer that. The example was just chosen in order to have simple periodical orbits. So I have just no idea. It was just constructed in order to be easy to make the integral around the paths.
Excuse me, who's talking?
Is Manuel Lines, the other author.
It's nice to see you, Manuel. I'm not sure we've ever actually met any closer than this. We've had lots of email correspondence, but
yeah.
I don't know, is Christina here too?
Yeah, she's here, but I don't know exactly where.
Okay. Anyway,
I can unmute her.
Okay, I was muted.
Yeah, and you should
oh, there you are. Hi, Christina.
Hi.
So I hope I did justice to our paper.
Well, one remaining question that you inspired, this is Jim, by the way. Alberto in particular has this notion of Poisson infinity, so to speak. Anybody looked at the relation of that to what you're talking about?
Is this Poisson infinity means like the graded algebra version of Poisson? I think that's what Chun Chun was asking about.
That's what it sounded like. I just wanted to tie down the connection better.
Yeah, as I said, I don't know.
Alberto,
I don't know what the connection is.
There is a comment by Dima. Dima is here. Dima, do you wanna speak and ask your question?
Oh, good.
Hi.
Hi, Dima.
Yeah. Hi, everyone. Hi, Alan. Yeah, the question was if there is still a non-closed three-form mapping to pi bracket pi, or not even that. Did you hear that? Am I coming through okay?
Go on. Yeah. Oh, is that the end of the question?
Oh, yeah. Yes, that was the question. Is there a non-closed three-form mapping to pi bracket pi, or you know, not even that?
That's a good question. Maybe in general, even on an almost Lie algebra, can you construct the dual of it? Can you construct a non-closed three-form? Or can you, maybe there's a three-form that's sort of naturally constructed, which turns out to be closed in certain cases, which you can catalog. I don't know. It's, again, I think it's an interesting question. So I think there are two kind of directions of questions. One is just the general geometric picture. What's going on here? How special is our example? And the other question is more back to the original physics problem. So I mentioned Maxwell-Vlasov equations. The equations that I wrote down on this dual of the Lie algebra are what's sometimes called Poisson-Vlasov, although this use of Poisson refers to something completely different from Poisson brackets. It's the Poisson equation that relates an electric potential to the charge density. It's basically a non-homogeneous Laplace's equation.
Right.
So in the full Maxwell-Vlasov equations, you have these charged particles moving around, generating their own electromagnetic fields. And so the electromagnetic fields satisfy the Maxwell equations with not in empty space, but with a density of charge and in our case, the density of monopoles. And without the monopoles, that was the example that Phil and Jerry and I found. And Phil, in his talk a couple of years ago, observed that those full equations did not satisfy Jacobi. Right? It was well known already, but he talked about consequences of that. And there's still some hope that by throwing in Maxwell's equations that somehow erases the failure of Jacobi, and that these full Maxwell-Vlasov are still twisted Poisson. And I don't know if Christina, or I don't know if Paula's there, if you want to say anything, or I don't want to put you on the spot, but if you want to say anything, your latest conjecture about what might happen there?
We are not really sure. We're still trying to construct this three form, and we have something, and I hope that we can clarify this soon, because I was actually working on it today. So I will keep you updated soon.
Okay, great. Well, I guess I've taken enough time, so that's all I have to say, except for I'm happy to hear more questions or stick around for a bit of a social hour.
Okay, let's thank, and then we'll have some more questions. Let's thank Alan. There has been a lot of interesting and very rich chat, and people are answering questions that's been in the chat. But if some of the people in the chat that have been adding information in the chat want to speak, just let me know, raise your hand, and we can have more questions. And I'll try to see you when you raise your hand. You can raise your hand if you go down when you look at the participants, and there is a way to raise your hand, or put a chat and I'll see you. Questions? Seems there are no more questions. Maybe Phil wants to add some information, or Phil Morrison.
Yeah, I just figured out how to unmute. I guess I don't have really much to add at this point. I'm also thinking about a lot of things, but nothing yet to report.
Okay. More comments, questions? Okay, if not, I mean, this was a very rich discussion towards the end. Let's thank Alan again, and we can stay for a while here connected, chatting. Thank you, Alan.
You're welcome.
Can I don't know how to raise my hand.
Yeah, okay. Yeah, sorry, Robert. Yeah, Robert has a comment indeed.
Yeah, sorry, I had to unmute myself just to barge in. I just noticed, I didn't understand much of the talk, I have to admit, but I noticed that the counterexample used a monopole density, which is essentially just x, the x coordinate, or x1, in your three-dimensional space xyz, or x1, x2, x3. And so that has a symmetry, of course, in the y and z directions. And it made me wonder whether the equations of motion are solvable. One of the things that Jeffrey and I have managed to do is to solve the equations of motion for a monopole density, which is rotationally invariant. Actually, is uniform. That's the only example we got. A sphere of monopolium. So this is integrability in probably the oldest sense of all, meaning that you can write the solution explicitly in terms of some reasonable functions. Of course, normally in Hamiltonian systems, you say it's integrable if you've got a complete set of conserved quantities, and that in turn reduces things to quadratures. I mean, that's the usual definition of integrability. But the sphere of monopolium is integrable in a sense of the nonlinear equations can be converted by means of a non-trivial transformation, can be converted into a linear system, which is solvable explicitly in terms of reasonably simple functions. So it made me wonder, in looking at that monopole density of yours, which is basically rho equals x, I think Alan called it phi. Phi equals x.
Yeah.
Phi of x, y, z equals x.
Mm-hmm.
It made me wonder whether the equations of motion are solvable for that system. And if it's related to the translational invariance in the x and y directions. I mean, the connection between symmetries and invariance only works, as far as I know, it doesn't work in these examples where you don't have Jacobi identity. That connection gets broken. But yet there's indications, maybe from this one example that Jeffrey and I have, that there's still something there connecting symmetries and solubility. Anyway, I just want to throw that out as a possibility.
Yeah, that's an interesting observation. It makes me wonder. I don't remember whether we looked at your example as to when we were searching for something that wasn't twisted Poisson, but it may be worth looking back at your example too, to see if we can generate. Remind me in your work with what you found with Jeff, Were there any periodic orbits? Were there many periodic orbits to speak of? Or they're mostly helical orbits, I think.
They were mostly helical type things. They, of course, so the monopole distribution we considered was a constant density with the rotational invariance. So it could be a sphere of, we thought of as a sphere of monopolium, perhaps outside of which there are no monopoles. And that's one model. Or it could extend to infinity. It could be uniform everywhere. If it's a finite sphere, then outside the magnetic field then you're dealing with the problem of a charged particle in the field of a Dirac monopole, because outside it's just the Dirac field. It's basically a Coulomb field, but it's a magnetic field instead of an electric field. And out there, the orbits lie on cones. This is a Poincare solution for that problem. Dates from 1896, something like that. But inside the sphere of monopolium, the orbits, of course, are modified. And in particular, you don't have the magnetic moment anymore. And you don't have the usual notions of conservation of magnetic moment that applies in guiding center theory, for example, which itself is only an approximation, but that no longer holds either. So you don't have constant magnetic flux through a loop. Anyway, to make a long story short, they're not periodic orbits. They're more like orbits on cones, that sort of thing. The solution is ultimately given in terms of parabolic cylinder functions. These are solutions of a linear equation. The nonlinear equations of motion, what Jeffrey and I did was transform them into a linear system, which is equivalent to a quantum harmonic oscillator with an upside down potential. And the solutions are standard special functions, parabolic cylinder functions, also called Weber functions. So, but anyway, just looking at that, just seeing that example just made me wonder, well, my goodness, maybe we got to think about a slab of monopoles, or, where there's a symmetry in the X direction, or X and Y directions, or Y and Z directions or something, just to see if that's solvable too. I mean, the question ultimately is there some relationship between symmetry and solvability in distributions of monopoles? The solution we got, by the way,
probably should have.
Excuse me.
Oh, I'm sorry to interrupt, but I probably should have introduced Jeffrey at the beginning, who defended his thesis yesterday.
Are you here, Jeffrey?
Yeah.
Yes, I'm here.
He waves
I'll
his
raise my
hand. You'll
hand.
recognize.
Okay, good.
I don't see you. Let's see. I got more face.
I don't think we've ever met either.
Oh, there's Jeffrey. Hi.
If you start talking, you'll come up on something.
Yeah, so unless, at least for the sphere of monopolium, unless you start out with zero velocity, all of the orbits are unbound.
All the orbits are, sorry.
Unbound. They go to infinity for time goes to plus or minus infinity.
So there are no, and if you start with zero velocity, you stay there. So, so there are no periodic orbits that we could use to use our method to.
Correct. Yeah.
Well, no. Wait a minute. No, that's with the. That's using a particular Hamiltonian. We also chose a weird Hamiltonian. We choose a weird. You get to choose the F also in addition to the magnetic field. And if you take F to be something other than the standard kinetic plus potential Hamiltonian, then it's possible we could get something with periodic orbits.
Yeah.
Right.
There are lots of things to try.
Yeah, and just looking at the chat, there isn't a Lagrangian formulation with monopoles. And I can find some papers that, go into that more detail if you're interested. So the plasma physics problem doesn't come from a variational principle.
Yeah, another question from Jair. Is there an holonomic mechanics analog to this? So, whole universe of questions. Very inspiring talk, Alan.
Well, thank you. I hope that something comes of it. As I said, one of the things I hadn't even thought about it until preparing the talk, that this really goes back to, I hate to say it, it's almost 40 years to my initial interest in Poisson geometry, which comes from Phil and Robert, both of whose pictures are on my screen right now.
It's like,
And that was, I should also give credit to someone else who is not here, Alan Kaufman, who was the thesis advisor of Robert, and who was running a seminar, I think originally at Lawrence Berkeley Laboratory, on plasma physics. And Jerry and I went up to that seminar, and that's what got us going on this whole business. And from there to Poisson geometry and Dirac structures.
Yeah, those were good times.
yeah, this is like old home week.
Okay, our Zoom manager is telling us to recall that next week we have the talk by Brent Bean, no? Next Thursday.
Yes.
And well, I mean, there is a lot of, I mean, we could go on talking for a long time because there's a lot of interesting questions that have been posed, and maybe we should ask for answers next week after the next talk, so to know if people did the homework. But maybe it's a good point. Maybe it's a good point to stop now. And well, first thanks Alan again. Thank you, Alan, for this.
Well, you're welcome. And I'm very glad to have this chance. I was a little afraid of doing, this is, as I said, this was the first talk of this kind, and my handwriting on the iPad is not so great, but I hope that everything was readable. So
That was great. Nice. It was really great.
Very inspiring. Maybe